Hello, I'm happy to present our work on stateful distributed FaaS from edge to cloud with Enoki. When we think about the edge to cloud continuum, we think about distributed heterogeneous resources that are geographically distributed, running a diverse set of tenant services, all the way from central clouds with infinite resources to the constrained resources at the edge. Serverless or function as a service is a great way to run tenant services at the edge and on the cloud because it allows us to have elastic resource allocation, which is great for the constrained edge, isolation between tenants, some infrastructure abstraction, which is crucial in such a diverse, heterogeneous, distributed system. And it allows us to do transparent invocation at the edge, which means when a client connects to some edge device, let's say gateway wants to run a service, they can do so transparently without having to know about any of the infrastructure that's behind the scenes, because there's this event-driven abstraction in serverless. When a client moves, we can just the client can just invoke a service at a different location using the exact same abstraction without having to care about routing, moving application services, etc. However, FaaS has a drawback, which is that only stateless services are supported. You might remember that FaaS is mostly event-based, has elastic scaling based on invocations, but that requires that only stateless services can run in there. So short-lived processes that carry no state between two invocations. But that is kind of a hindrance for a lot of edge services because often we want to leverage both the benefits of FaaS at the edge or also having some stateless, stateful applications. For that, what we do in the cloud at least is we say, okay, we simply add a database. So let's say we do this at the edge. We have a client that connects to some Lambda running at some edge location. That Lambda has to then pull in state from some database, which looks great in the cloud. But if you have this additional latency to the cloud from the edge, then you basically lose all the benefits of edge execution. So you might say, okay, actually, let's just add our database to the edge location instead. We co-locate our functions with our databases. The client connects to some function, lambda1, at a specific edge location. There's a backing data store that's local, and the client immediately receives a response with low latency without additional round trips to the cloud, which is great. But now let's say the client is moving. The client is moving to a different edge location. That's the same invocation. The client doesn't know about, that there's other infrastructure that's now handling the request. To a second function, which is still an identical function, but now a different edge location. It's just pulling the state from the first edge device, let's say gateway or some other edge server, and gets the data from there. We call this a peer read, based on a peer-to-peer system because the edges collaborate directly. So you get your result back, function execution is successful. However, we now again lose all the benefit of X execution because we have this additional latency to that backing data store. Instead, we are proposing a replication-based approach. So we have, let's say, two function locations, and both have a data store that's co-located with them. The client makes a request. It's answered directly from a local data store at the edge device, at the edge node. And in the background, there's an asynchronous replication to the second location. So wherever your function is deployed, you can add the data store and have replication. And now when the client moves to a different location, it transparently can access an identical function at a different location, but with the same backend data, but locally without having to move this extra array for every invocation. And this way, we always have backing data available locally in our edge FaaS system. This is what we did to implement it. We call this Enoki. You're combining basically a FaaS platform with a replicated key value store. So this is how it works. It's all open source. You can check out the prototype on GitHub. We have a node that's running our Enoki middleware. And we have on the one hand our FaaS system, which is some edge FaaS system for constrained resources at an edge node, maybe even a cloud node. And each Lambda that we run on this FaaS system has a local middleware, a client library that can access the data for that specific function. So function A, for example, from a co-located key value store. So let's say we have a bunch of replicas of function A that can concurrently handle requests for that function at that node. And those can all access their backing data from the key value store. Now in the background, if we have another node that can run an identical function at a different location, and we simply do replication between our key value store. Supporting all of this is a key value configuration service that sits in the cloud that is basically about configuration metadata exchange between the different nodes as a centralized service. So this is what the interface could look like. We simply import a library that has all the access methods and APIs that we need to a function. And we have this function header, typical serverless function header that just you define a function that's invoked for every call to the FaaS platform for that specific function. And that's an input and an output. Our library has a simple get interface. You can get a current key. You can do whatever you want with your data. It's a key value store, so you can modify it, you can read it, you can do calculations on it. In this case, you simply append a string. And you can then also use a simple set interface to set a different value and save all the modifications and save your new state. The building blocks that we use for this, on the one hand, is TinyFaaS, which is a edge-based, lightweight serverless platform, FaaS platform that we developed. It's simply based on Docker that has a lightweight reverse proxy at the beginning and simply has a bunch of function handlers. So this is what we use as a FaaS building block. On the other hand, we also have Thread, which is a distributed key value store. Both of those systems were previously published. Thread allows you to do application-controlled replica placement throughout the edge cloud continuum. So when you have a bunch of nodes that are geographically distributed, like from cloud intermediate nodes to edge gateways or mobile access edge computing, you simply deploy our software and an application can control the replication of so-called key groups, which are logical encapsulation of data. And through the client library that I invoked earlier, applications can access their data at different locations and can simply specify at which location data copy should be kept. So we put this together and let's see how it works. We did a bunch of evaluations that you can find in the paper just to give you some impression of what happens. Here's a simple basic example where we run a function that calculates a moving average on data. So we have our function header, we import our library, and we have we get a current pointer to where in the buffer we currently are. We increment it by 1. We have to store the new value, the new sensor value that we get from some edge device, store a new pointer, then get the 10 most recent values from our database. So this is the backing state, and return basically the mean or average of those values. So this is how we both save the data that's incoming from a sensor, but also return the average of the 10 most recent values. So it's fairly standard kind of IoT application that traditionally, if you wanted to implement it with FaaS, even though it's basically very much event-based, would be difficult because it relies on this on keeping state between invocations. We deployed this with Enoki on this very basic edge to cloud infrastructure. We have a client that sits near an edge device, near an edge server that has more limited resources with a 2 millisecond round trip time. And then we have a backing cloud, which is a bit further away, has a bit better network connection. And we're basically comparing, locating, so we have Enoki running at the edge, comparing if we store our data locally or if we store it in the cloud as a backing data store. And of course, what you will see is there's a 200 millisecond increase in the request response latency for our client, simply because we have 4 key value operations that we do. And each of those in the cloud, which is this line here, adds a 50 millisecond delay. So you have basically the same performance, but we simply add a 4 times 50 millisecond latency, which is terrible, and you don't want that because that basically destroys all the benefit of edge computing. Of course, the elephant in the room is consistency. Every time you do some form of application, especially in geo-distributed, heterogeneous environment, if you have, an unreliable internet below that, you have to care about consistency. The thread building block that we developed allows for client-centric consistency, but the clients in this case are a function. So a function running on a specific edge node, that is our client. So this function will never see outdated values. It will always see also values such as red, to have monotonic reads, monotonic writes, and read-your-write consistency, which is fairly easy to implement because we co-locate our key value store with our function as a service platform. So that means a function on that node will always access the same copy of the data. However, of course, we have to trade consistency for availability in network partitions. We don't want our distributed FaaS platform to completely break down if two nodes can't communicate. So if you have some form of network partition, that consistency has to stop. We also did some data staleness evaluation, and you can find in the paper. Of course, if you have a single data store that's somewhere in the cloud or at the edge and you do peer-to-peer reading, you don't have any staleness issues because there's no application at all. But if you do replication and you don't do strong consistency, which needs some form of consensus, which can add additional latency, then you have to trade staleness for that. One thing that we plan to do in the future is maybe explore a bit more the possibilities of using conflict-free replicated data types to, support applications in a more conflict-free replication logic. So you don't run into any logical issues because of the backend replication when the client moves, accesses a function at some edge node. So we always have that kind of consistency, maybe on that level. To conclude, I told you FaaS is great for the edge, but the stateless model of FaaS is a bit of a deal breaker for some applications, for a lot of applications. So we decided to add state to FaaS on the edge to cloud continuum, which is non-trivial because it requires replication. And we saw that with Enoki, the replication strategy that we have beats both peer-to-peer and central cloud data sinks. In the paper, you'll also find the GitHub link. It's here for your convenience as well. Feel free to check it out online. And that concludes my talk. Thank you.